Okay, so today we're going to be talking about statistical significance. What does it mean? Let's go to the definition. A set of measurements or observations in a statistical study is said to be statistically significant if it is unlikely to have occurred by chance. We've got several examples on the next couple of slides to kind of explain this a little bit more to you guys. A detective in Detroit finds that 25 of the 62 guns used in crimes during the past week were sold by the same gun shop. And that's a very high proportion. So it's unlikely to have occurred by chance. Global temperatures. The 15 years from 2001 to 2015 were 15 of the 16 hottest years on record. Up to 2015, using records going back to 1880. So having 15 of the 16 hottest years on record occur in a single 15-year period is statistically significant. And it might be a hot streak, and it's very unlikely to have occurred by chance alone, and it may be indicative of a heating world. The team with the worst win-loss record in basketball wins one game against the defending league champions. Okay, so this is not statistically significant because although we expect a team with a poor win-loss record to lose most of its game, we would also expect it to win occasionally, even against the defending league champions. Okay. Now we're going to consider statistical significance in experiments. A researcher conducts a double-blind study. Remember, that's where neither the experimenter nor the subjects know who gets what treatment. It's about a herbal formula, and it is effective in preventing colds. During a 3-month period, 100 randomly selected people in a treatment group take the formula, while the 100 randomly selected people in the control group take a placebo. Remember, a placebo is an innocuous medication, has no medicinal value, but it looks, tastes, feels, smells. It looks exactly like the actual medication. The results show that 30 people in the treatment group get colds compared to 32 people in the control group. Can we include that the formula is effective in preventing colds? Okay. Well, first of all, whether you get a cold or not can be dependent on many different factors. So you should not expect the number of people with colds in any two groups of 100 people to be exactly the same. The difference between 30 people and 32 people seems small enough to be explained by chance. So the difference is not statistically significant. So we should not conclude the treatment is effective. Okay, so how do we quantify statistical significance? The definition of statistical significance that we've been using before is too vague. We need a way to quantify statistical significance. In general, we've determined statistical significance by using probability to quantify the likelihood that a result may have occurred by chance. We ask a question like this one. Is the probability that the observed difference occurring by chance is less than or equal to 0.05 or 1 in 20? So this is the cutoff they use in statistical studies. 5% of the time, 0.05 is the probability that the observed difference occurred by chance less than or equal to 0.05. Okay? If the answer is yes, the probability is less than or equal to 0.05, we say that it is statistically significant at the 0.05 level. And you'll see this in statistical literature or academic journals, okay? They compare it to that 5% level. You could compare it to 10%, you could compare it to 1%, or more commonly, it's 5%. If the answer is no, the observed difference is reasonably likely to have occurred by chance, we say that it is not statistically significant. It's kind of arbitrary what number you pick. 0.05 is used most commonly. You could get 0.1 or 0.01. Okay, if the probability of an observed difference occurring by chance is 0.05 or less, it is statistically significant. If it is 0.01 or less, the difference is statistically significant at the 0.01 level. Okay, in the test of the Salk polio vaccine, 33 of the 200,000 children in the treatment group got paralytic polio, while 115 of the 200,000 in the control group got paralytic polio. Precise calculation by researchers showed that the probability of this difference between the groups occurring by chance to be 0.0000002%. So is it significant? And the answer is yes. It is statistically significant. It is definitely lower than that 5% threshold or even at the 0.01 level. It's highly significant, statistically significant. So the results of the polio vaccine test would be statistically significant at the 5% level and at the 1% level, because the actual probability of them occurring by chance was calculated to be, you can see it there, the results are certain significant at 0.05 and 0.01. Okay, so that's 6.1. Now we're going to go to 6.2. Okay, going into probability a little bit more. Okay, we're going to learn how to quantify probabilities in this section. Okay, so let's consider one of the basic ideas in probability, tossing two coins. There are 4 different ways the coins could fall. You could get heads, heads. You could get tails, tails. You could get heads, tails. You could get tails, heads. So in flipping 2 coins, you could either get 0 heads, 1 head, 1 head, or 2 heads. Okay? So we're only interested in the number of heads because the 2 middle outcomes have 1 head. We say that these 2 outcomes represent the same event. It shows there are 4 possible outcomes. You could get 0 heads, you could get 1 head, you could get 2 heads. Okay? Definition: an outcome are the most basic possible results of observations or experiments. So when you flip 2 coins, you can get heads, tails, that's an outcome. Tails, heads is another outcome. An event is a collection of 1 or more outcomes. The sheer property of interest. So for example, if you toss 2 coins and count the number of heads, the outcomes heads, tails, and tails, heads, both represent the same event of 1 head. Okay? So this gives us the idea of what a probability is. The probability of an event is a decimal, or you can refer to it as a percent, but most commonly it's referred to as a decimal. It's a decimal between 0 and 1 inclusive, including 0 and including 1. A value of 0 is impossible, can't happen. A probability of 1 is certain. Okay, 0.5 would be in the center of the spectrum, and that's a 50-50 chance. So it's very unlikely if it's close to 0, very likely if it's close to 1. Okay, now how do you calculate probabilities? There are 3 methods we're going to talk about: the theoretical, the relative frequency or experimental approach, and the subjective approach. Let's go to theoretical. Count the number of possible outcomes. Among all possible outcomes, count the number of ways the event A can occur. Take the probability of A as the number of ways A can occur, divided by the total number of outcomes. That's the probability of A. Theoretically. So suppose you select a person at random from a large group at a conference. What is the probability that the selected person has a birthday in July? Okay, well, think about it. How many days are there in July? Well, this is how I always remember it. 30 days has September, April, June, and November. When short February is done, all the rest have 31. So that means July has 31. So 31 out of a total of 365. We're assuming each day is equally likely. Okay? 0.0849. So slightly more than 1 in 12. Okay? Okay, so suppose we toss 2 coins and we want to count the total number of outcomes. The toss of the first coin has 2 possible outcomes, heads or tails. Second, 2 possible heads or tails. The 2 outcomes of the first coin can occur with either of the 2 outcomes or the second coin. So the total number of outcomes are 2 by 2. You've got 2 outcomes for the first possibility, 2 outcomes for the second toss. 2 times 2 is 4. So here on the next slide, we will see a tree diagram. A tree diagram is a great way to illustrate a probability experiment. You follow it out from the node, the initial node, out the branch to find the probabilities. Okay? So here's an example. Tossing 2 coins, tossing 3 coins, 2 or 3 coins. On the left-hand side, you've got a probability experiment of tossing 2 coins. On the right, you've got an example of tossing 3 coins. You can start at the basic node, where on the leftmost part of the graph it is, and you follow it out the branch. Okay? Then you can list all possibilities for your outcomes. Okay? So there's 2 possibilities on each toss. 2 times 2 times 2, if for 3 tosses of the coin, is 8 possibilities. What about 4 tosses? 16 possibilities. What about 5 tosses? 32 possibilities. You see the pattern here? It's 2 outcomes for each toss. 2 times 2 times 2 is 8 for 3 tosses. Okay? Okay. So now we're going to talk about counting outcomes. Suppose process A has a possible outcomes, has A possible outcomes. The process B has B possible outcomes. Assume they don't affect each other, and the number of different outcomes for the 2 processes combined would be A times B. What if we've got A, B, and C? A times B times C. You multiply the number of outcomes for each process together. Okay, how many outcomes are there if you roll a fair die and toss a fair coin? So let's think about this, okay? Roll a fair die and toss a fair coin. There are 6 possibilities for a fair die, and there are 2 possible ways to flip a fair coin. 6 times 2 is 12. Okay? I think that it looks like in this example of they're considering 2 dice here, even though it says here, roll a fair die and toss a fair coin. If you're rolling a fair die and then tossing a fair coin, then you're going to have 12 outcomes. If you're rolling 2 die, you're going to have 6 times 6 is 36. What is the probability of rolling 2 ones? Well, think about, the sample space. You get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. That's 1 outcome out of 36. How do we get the 36? 6 outcomes per toss of the die, per roll of the die. 6 times 6 is 36. So 0.0278. Okay. Now we're going to talk about having what is the probability that a randomly selected family with 3 children has 2 girls and 1 boy? Okay, so here we're going to list out all the possibilities for having 3 children. Okay, so you have 3 children. Each time you have a child, you've got either a boy or girl. So that's 2 outcomes per trial, or 2 outcomes per birth. And 2 times 2 times 2 is 8. So there's 8 possibilities total. You have to list them all out, and you have to count how many of them have 2 girls and 1 boy. And that's 3 out of 8, which is 0.375 probability. Okay, births of boys and girls are not equally likely. Naturally, there are approximately 105 male births for every 100 female births. Male death rates are higher than female death rates, so female adults outnumber male adults. Now we're going to talk about relative frequency, another way to compute probability. The second way is to approximate the probability of event A by making many observations and counting the number of times A occurs, is the relative frequency or empirical method. So what do you do in this? You repeat or observe a process many times and count the number of times the event of interest occurred. take the number of times it occurred and divide that by the total number of observations. Okay, geological records indicate that a river has crested above a particular high flood level 4 times in the past 2,000 years. What is the relative probability that the river will crest above the high flood level next year? Well, you take how many instances there are, and you divide by how many years there were. So 4 out of 2,000, 1 out of 500 probability. So it's very unlikely, 0.002. Now we're going to get to subjective probability. So that's a little bit different. Subjective probability is based on judgment or experience or intuition. It's the third method for determining probabilities is subjective probability using experience or intuition. So we have talked about 3 different ways to compute probability. Theoretical, based on assuming all are equally likely. Divide the number of ways an event can occur by the total number of possible outcomes. Relative frequency or empirical, based on observations or experiments, observation or experiments. It is the relative frequency of the event of interest. Subjective, based on experience or intuition. So let me just give you some examples of some subjective probabilities. Let's say you're trying to predict the chances of a recession next year. Okay, you say the chance of recession is 10%. That's a subjective probability because it's based on your judgment, your experience, your intuition. Another example would be like betting on horses. That would be a subjective probability. Weather patterns is also subjective. So identify the method that resulted in the following statements. I'm certain that you'll be happy with your new car. That would be subjective. Based on the housing data, the chance that someone will move to a new residence during the coming year is about 1 in 8. That's empirical or relative frequency. The chance of rolling a 7 with a 12-sided die is 1 over 12. That is theoretical. So here, subjective, relative frequency, theoretical. Okay. So we have talked about the probability of an event occurring. What about the probability of an event not occurring? Well, it turns out that the sample space, in the sample space, it either is an A or is not an event A. It is an event A or it's not an event A. So you can think of the complement as 1 minus the probability of A. So the complement of an event A, the not A, is often designated by a bar. So we've got A bar means not A. Okay, we can skip this slide. Okay. Okay, so here we've got the probability distribution for the number of heads when tossing 2 coins. Okay, it gives all the outcomes and the probability of it occurring. That's a probability distribution. Okay. Another way to express likelihood is to use odds. The odds against an event are the ratio of the probability that the event does not occur to the probability that it does occur. For example, the odds against rolling a 6 with a fair die are 5 6 times 1 6 or 5 to 1. The odds using gambling are called payoff odds. They express your net gain on winning bet. For example, suppose that the payoff odds on a particular horse at a race are 3 to 1. That means for every $1 you bet on the horse, you will gain $3 if the horse wins and get your original $1 back. So how do you make a probability distribution? A probability distribution represents the probabilities of all possible events. So do the following to display it. List all your outcomes. Use a table or a figure. Identify outcomes that represent the same event. Find the probability of each event. Make a table in which the column lists each event and another that lists the probability. Sum of the probabilities, remember, has to add up to 1 because it's a sample space. Has to add up to 1. It represents all possible outcomes. Okay, so here, make a probability distribution for the number of heads that occur when 3 coins are tossed simultaneously. Well, again, 2 for the first toss, 2 for the second toss, 2 for the third toss. 2 times 2 times 2 is 8. 8 possibilities. Count how many involve 0 heads, 1 head, 2 heads, 3 heads. Count how many of the outcomes are in each of these possibilities. Make a table. So here we've got number of heads, 0, 1, 2, 3, and 3 tosses, and the resulting probability. When we add up our fractions here, we get 1. Okay. Here's an example of tossing 2 dice or rolling 2 dice. The 36 outcomes, we've already talked about that because you've got 6 on the first roll, 6 on the second roll. 6 times 6 is 36. You can list them all out in a table form by going 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, all the way through 6, 6. Okay? This table can be easily computed. Then you're going to count the sum on each of the 2 tosses, make a table, and count how many of the 36 have that sum. That probability will add up to 1. You can graph this. We can see it's symmetric. The peak is at peak sum is at 7. Okay. Okay. So that's 6-2. We're going to go on here to the next slideshow. Let me pull this up. Okay, now we're talking about probabilities with large numbers. So we're going to talk about the law of large numbers, understand expected values, and how misunderstanding of the law of large numbers leads to gambler's fallacy. Okay, what is the law of large numbers? Let's explain it a little bit more. It applies to a process for which the probability of an event A, P of A, and the results of repeated trials do not depend on the results of earlier trials. That is, they are independent. It states the following. If the process is repeated through many trials, the portion of trials in which event A occurs will be close to the probability of A. The larger the number of trials you make or you perform, the closer it is to get to the true probability of A. So it means if we do an experiment and we keep repeating it over and over again, the more times we repeat it, the closer and closer it gets to the true probability. Okay? That's the law of large numbers. A roulette wheel has 38 numbers. 18 are black, 18 are red, and 0 and 0, 0 are in green. So there are 38 outcomes. What is the probability of getting a red number on the spin? Well, there are 18 red numbers. 18 out of 38 is 0.474. Okay? Okay, if patrons in a casino spin the wheel 100,000 times, how many times did you expect a red number? Take your decimal from the previous slides, 0.474, and multiply by 100,000. And you get 47,400. 47.4% of the time. Now we're going to talk about what's called an expected value. The expected value of a variable is the weighted average of all possible values. Because it is an average, the expected value is likely to be close to the actual value only when there are a large number of events, so that the law of large numbers comes into play. Okay? You could think of an expected value as a weighted mean, is what you can think of it as. Think about when you calculate your grade for a course where you've got weighted grade, not based on points, or if you're calculating your GPA, it's like a weighted mean. Okay, then you can think of it as a weighted mean. Okay, so calculating an expected value, here's how you go about doing it. Consider 2 events, each with its own value and probability. You're going to take the value of event A times the probability of event A plus the value of event B times the probability of event B. It can be extended to any number of events by including more calculations. Okay, suppose that $1 lottery tickets have the following probabilities. A 1 in 5 to win a free ticket worth $1. a 1 in 100 to win $5, 1 in 100,000 to win 1,000, and 1 in 10 million to win 1 million. What is the expected value of the lottery ticket? So winners do not get the dollar they spend back on the ticket. Okay, we're going to make a table. Okay, so you're going to have your event, your value, your probability, then your value times probability. 1 times 1 is 1. Now remember, if you purchase a ticket, it's gonna cost you $1. So that's a loss of $1 to you. So -1. If you win a free ticket, you're gonna have a +1. If you win $5, you're +5. Win 1,000, you have +1,000. Win 1,000,000, you've got 1 million. Okay, so you're going to take your value times the probability and add up this last column here. Okay, and you get an expected value of -0.64. Thus, averaged over many tickets, you would expect to lose 64 cents for every lottery ticket that you buy. If you buy, say, 1,000 tickets, you're going to lose $640. Now let's talk about gambler's fallacy. It's a mistaken belief that a streak of bad luck makes a person due for a streak of good luck, or that a streak of good luck will continue. Okay, so you're playing the coin toss game in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you have 45 heads and 55 tails. You continue play until you've tossed it 1,000 times, at which point you've got 480 heads and 520 tails. Is this result consistent with what you expect in the law of large numbers? Okay, have you gained back any of your losses? Explain. The proportion of the heads in your first 100 tosses was 45%. After 1,000 tosses, the proportion is 48%. Because the proportion of heads move closer to 50%, it's consistent, right? The more times you repeat an experiment, the closer and closer it gets to that true probability. So that is consistent here. However, now you've won $480 and lost $520 for a net loss of $40. Your losses increased despite the fact the proportion of heads closer to 50,000. So let's talk about streaks a little more. A common misunderstanding that contributes to the gambler's fallacy is expectations about streaks. Okay, so consider this example. Do you think it's more likely to see the outcome heads, 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 or heads, tails, tails, heads, tails, heads? It turns out they're exactly equally likely. Okay, it doesn't matter which ordering you get, exactly equally likely, because on every single toss you have 2 possibilities to get either a heads or a tails. Most people would say the latter is natural while the streak of all heads is surprising, but in fact they're equally likely. Remember, each flip a coin, you've got 2 possibilities. 2 times 2 times 2 times 2 times 2 times 2 is 64. So 1 out of 64 possibility. Suppose you just tossed 6 heads and then bet on the outcome of the next toss. You might think that given the run of heads, a tail is due. But again, the probability is still 50%. Doesn't matter what you had previously. Every time you toss a coin with a fair coin, you have a 1 out of 2 probability. Okay? Okay, planning for rain. A farmer knows that at this time of the year, in his part of the country, probability of rain on a given day is 0.5. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified to postponing irrigation because he is due for a rainy day? Okay, so the farmer's having a losing streak. 10-day dry spell is unexpected. We assume the weather events are independent from each other, which is not often the case, not always the case. Then the probability of rain is still 0.5 on any given day if he's not due for rain. Okay, so that's that one. Got one more presentation here. Okay. Okay, now we're going to talk about combining probability. Independent dependent, overlapping, non-overlapping, and do some calculations here. Okay, suppose you toss 2 fair dice. Okay, we're going back to the dice. We want to know the probability that both will come up with 4. Well, there are 6 possibilities on a dice. So 1 out of 6 possibilities of getting a 4. You're doing it twice, so 1/6 times 1/6 is 1 over 36. We call this an AND probability because the event A and event B, getting a 4 and a 4. So you multiply those individual probabilities together. Okay? 2 events are independent if the outcome of one event does not affect the probability of the other event. Consider 2 independent events, A and B. We would take probability of A and B equals probability of A times probability of B. In probability, and means multiply. The principle can be extended to many events. If you want A, B, and C, it'd be probability of A times probability of B times probability of C for however many events you have, assuming they're independent. So you've got 3 coins this time. What is the probability of getting 3 tails? Well, getting tails is 1 over 2 in each toss. 1 over 2 times 1 over 2 times 1 over 2, 1/8. Okay? Okay, so this is describing this. A batch of 15 memory cards contains 5 defective. What is the probability of getting a defective card on both the first and the second selection? Okay, this is a little bit different because you're drawing from a pool of memory cards and you're taking one away. So these 2 events are not independent because your probability is changing. 5 over 15 times 4 over 15, 4 over 14. Just decrease the numerator and the denominator because you already took one away. You already had one defective, 0.0952. So 2 events are dependent if the outcome of one event affects the probability of the other event. Probability that dependent events A and B occur together is probability of A times probability of B given A. And it can be extended to multiple events besides just 2. Probability of B given A is called a conditional. In some books, they call it probability B and then a vertical bar A. So it's conditional probability. Okay. A polling organization has a list of 1,000 people for a telephone survey. The pollsters know that 433 people out of the 1,000 are members of the Democratic Party. Assuming that a person cannot be called more than once, what is the probability that the first 2 people called will be members of the Democratic Party? Okay, so it'd be 433 out of the 1,000 times 432 divided by 999. Take 1 away from the numerator, 1 away from the denominator. Okay? And that is your probability. Okay? If they're independent, meaning it doesn't matter what you got on the previous call, then you don't reduce the numerator, you don't reduce the denominator, and you get a different probability. If relatively few items or people are selected from a large pool, then dependent events can be treated as independent events with very little error. A common guideline is that independence can be assumed when the sample size is less than 5% of the population size, and it's used by polling organizations. Now we're going to talk about either or probabilities. Okay, so consider a Venn diagram. I'm sure you've seen this type of graph in your high school algebra or statistics classes. You've got 2 events, heads and tails. These are mutually exclusive or disjoint because they have no overlap. Okay, so these are 2 non-overlapping events. If you have non-overlapping events, you can take the probability of each event and just add them together. Because they have nothing in common, you don't need to worry about that. So probability of A or B is probability of A plus probability of B. Probability of A, B, or C is probability of A plus probability of B plus probability of C. Add the individual probabilities together. That's what you can do if they're non-overlapping, also called disjoint, also called mutually exclusive. Okay? Now you're rolling a single die. What is the probability of getting an even number? Okay? So that would be, an even number would be a 2, 4, or 6, 2 or 4 or 6, Getting a 2 is 1 over 6 probability. Getting a 4 is 1 out of 6 probability. Getting a 6 is 1 over 6 probability. 3 over 6 is 1/2. So probability of getting an even number, 2, 4, 6, add them together, 1/2 probability, or 3 over 6. Okay, to improve tourism between France and the United States, 2 governments from a committee consisting of 20 people, 2 American men, 4 Frenchmen, 6 American women, and 8 French women. Here's the table. If you meet one of these people at random, what is the probability the person will be either a woman or a French person? Either a woman or a French person, okay? So what you would do is you would do some calculations here. Probability of, you would take woman, probability of woman, plus probability of French, minus probability of woman and French. We would use a different rule because there is overlap between these categories. You could be woman and French as well. Okay, so we would take 14 out of 20. 14 comes from 8 plus 6. That's the women. Then you've got 12 out of 20. That's the probability of being French. Then you've got 8 people who are women and French. So you have to subtract that middle part off. Why? Because that middle part is getting counted twice. They're getting counted in the French people, and they're getting counted in the women. So they're getting counted twice. Okay? So this is a general addition rule. Probability of A or B is probability of A, plus probability of B minus probability of A and B for overlapping events. This is a summary. We've got all the different probabilities we've calculated, so you've got those to review, and that's it.